just matter. Remember, it's empty.
How do you know this is?
I read Dr. Quantum comics. Everybody thinks it's just kid stuff, but I know it's real. That's how I do my magic on the court.
So, what they taught us in school isn't really the way it is, and that our senses are playing tricks on us. You just gotta wonder, what is this reality that we find ourselves in? Quantum physics says it's all just waves of information. Do I believe that? I hope so. Yikes!
That's how I do my magic on the court.
Yeah, I always choose the Wonder Boy first.
Well, Dr. Quantum says everybody's got it. Everybody's doing it. Doing it constantly. Each and every time you look.
And here we are, the granddaddy of all quantum weirdness, the infamous double-slit experiment. To understand this experiment, we first need to see how particles, or little balls of matter, act. If we randomly shoot a small object, say a marble, at the screen, we see a pattern on the back wall where they went through the slit and hit. Now, if we add a second slit, we would expect to see a second band duplicated to the right. Now, let's look at waves. The waves hit the slit and radiate out, striking the back wall with the most intensity directly in line with the slit. The line of brightness on the back screen shows that intensity. This is similar to the line the marbles make. But when we add the second slit, something different happens. If the top of one wave meets the bottom of another wave, they cancel each other out. So now there is an interference pattern on the back wall. Places where the two tops meet are the highest intensity, the bright lines, and where they cancel, there is nothing. So, when we throw things, that is, matter, through two slits, we get this, two bands of hits. And with waves, we get an interference pattern of many bands. Good so far. Now, let's go quantum. An electron is a tiny, tiny bit of matter, like a tiny marble. Let's fire a stream through one slit. It behaves just like the marble, a single band. So, if we shoot these tiny bits through two slits, we should get, like the marbles, two bands. What? An interference pattern. We fired electrons, tiny bits of matter, through. But we get a pattern like waves, not like little marbles. How? How could pieces of matter create an interference pattern like a wave? It doesn't make sense. But physicists are clever. They thought, maybe those little balls are bouncing off each other and creating that pattern. So they decide to shoot electrons through one at a time. There is no way they could interfere with each other. But after an hour of this, the same interference pattern is seen to emerge. The conclusion is inescapable. The single electron leaves as a particle, becomes a wave of potentials, goes through both slits, and interferes with itself to hit the wall like a particle. But mathematically, it's even stranger. It goes through both slits, and it goes through neither. And it goes through just one, and it goes through just the other. All of these possibilities are in superposition with each other. But physicists were completely baffled by this. So they decided to peek and see which slit it actually goes through. They put a measuring device by one slit to see which one it went through and let it fly. But the quantum world is far more mysterious than they could have imagined. When they observed, the electron went back to behaving like a little marble. It produced a pattern of two bands, not an interference pattern of many. The very act of measuring or observing which slit it went through meant it only went through one, not both. The electron decided to act differently, as though it was aware it was being watched. And it was here that physicists stepped forever into the strange netherworld of quantum events. What is matter? Marbles or waves? And waves of what? And what does an observer have to do with any of this? The observer collapsed the wave function simply by observing.
We are always the observer. But sometimes we identify with the event so much so that we even lose the aspect of the observer. That's why the materialist gets totally lost and thinks that we could do without the observer.
The physics data tells us that an object itself is really a simplification for what we call out there. One is particularly when we're looking at atomic and subatomic particles or atomic and subatomic matter in any form. What we find is how we go to look at it, what we choose to examine it with, actually changes the properties of what we observe to be out there.
Is this the observer, and which is so intricate to understanding the wacky, weird world of quantum particles and how they react? Is this, then, the observer? And even though we cannot have a quantum field without the observation of scientists who have gone there, who have uncovered it, layer after layer after layer, they're all observers. But not one of them agree conclusively on all points in the field, because they are perceiving the field mathematically from different angles of perception.
We don't know in quantum mechanics how to hook ourselves as observers up with the world. We don't know how to treat ourselves as observers as just another part of the physical system that we're describing. The only way we know how to do quantum mechanics as it's traditionally formulated is to keep the observer outside of the system you're describing. The minute you put him in, you get all these paradoxes. And we're forced to say things in quantum mechanics like, look, the book is doing what it's doing because of quantum mechanics, and I see that because I'm there and I see it, and you better not try to analyze that second part of the sentence in terms of applying quantum mechanics to it, because it's going to break down. That's why there are these two separate laws of the evolutions of physical systems. One that applies when you're not looking at them, the other that applies when you are. But that's crazy.
There's no way that we're ever going to mathematize or put into mathematical formula this very act in which a conscious observer comes up with the answer. People say, oh, the measuring instruments, the recorder records it, and there it is. It's on the tape. It's recorded. You forgot one part of the equation. Somebody has to look at the tape. And until somebody looks at the tape, it ain't recorded at all.
When you are not looking, there are waves of possibility. When you are looking, then there are particles of experience.
A particle, which we think of as a solid thing, really exists in a so-called superposition, a spread out wave of possible locations. And it's in all of those at once. The instant you check on it, it snaps into just one of those possible positions.
It's easy to generate situations where the equations of motion will predict that, say, the wave function, the psi of a certain basketball, is uniformly distributed all over the basketball court. We don't have any idea what a state like that would look like. According to the law of quantum mechanics, that's supposed to be a state in which it fails to make any sense even to ask the question, where is the basketball? That is, according to the law of quantum mechanics, asking the question, where is a basketball whose psi is uniformly distributed over a whole basketball court, is the logical equivalent of asking about, say, the marital status of the number 5. Okay? It's not that you don't know the answer, you don't happen to know whether the number 5 is married or a bachelor. It's that the question somehow is radically inappropriate in the first place. The number 5 doesn't have a marital status. There's nothing there to ask about. And similarly, a basketball whose wave function was uniformly distributed over the entire basketball court would not have a position that could even coherently be asked about. Now, the crux of the measurement problem is precisely that, although the Schrodinger equation predicts under certain circumstances which we basically know how to reproduce in the laboratory, that basketballs should go into states like that, states where there fails to be any